Alright, so far we've talked about how we can find an address for our electrons and how we can write down that address in a more formal sense. We've talked about how the electrons would file into an atom and where they would sit and what addresses they would have. So the last things we need to talk about are a few just kind of miscellaneous ideas or pieces of information that we can get from an electron's address, and we'll talk just a little bit about what we might want to use those for. So quantum mechanics miscellaneous ideas. The first one is called valence electrons. And valence electrons, definition, are those electrons that are in the outermost or the highest number principal energy level. And we care about where these are or what these are because the valence electrons are the ones that are mostly responsible for bonding and reactions. And that's going to be our main topic of study for most of the rest of the year. So these are pretty important. And it's not too difficult to figure out how many valence electrons there are. It's basically just counting off of an electron configuration. You just have to know what to count. So electrons that are located in the highest or in the outermost principal energy level are the valence electrons. So we're just going to look at some examples. Let's do the electron configuration for nitrogen. Find your periodic table. Nitrogen has 7 electrons. And if we do the configuration count as we go through, we would have 1s2, 2s2, 2p, 3. 1s2, 2s2, 2p3. And you can see here that I've said that this element has 5 valence electrons. So where did that come from? Well, the valence electrons are in the highest number principal energy level. The energy levels are the big numbers in front, so we have a 1 and a 2 and a 2. The highest of those numbers is the 2. Then we count how many electrons are in the second energy level. There's 2 here plus 3 here makes 5. 5 valence electrons. Let's do another example. Here's chlorine. If you look at your periodic table, you'll see that chlorine has 17 electrons. So let's do the electron configuration. 1s2, 2s2, 2p6, now we're up to 10, we need 7 more, 3s2, 3p5. And again, look for the highest energy level. We have a 1 and a 2 and a 3. 3 is the highest, so we add up the electrons that are in the 3. There's 2 plus 5 makes 7 valence electrons. One more. Let's do zinc. Check your periodic table. Zinc has 30 electrons. 1s2, 2s2, 2p6, that takes us up to 10, 3s2, 3p6, 4s2, now we're at 20. And how many electrons can a D sublevel hold? 3D comes next. It can hold up to 10, and that's actually what we need it to hold. So 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Check the energy levels. 1, 2, 3, 4. The highest number is 4. How many electrons are in the 4? 2. So zinc has 2 valence electrons. Miscellaneous idea number 2. Again, because of bonding and because of reactions, it is sometimes helpful to know how many unpaired electrons an atom has. And unpaired would just mean single electrons in the electron configuration. So to figure this out, we actually need the orbital diagram. Remember, the orbital diagram was the picture with the circles, and you had to put the electrons in the circles kind of like we put them in houses back at the beginning. So use the orbital diagram to count the number of paired and unpaired electrons. Again, it's just counting, you just have to know what to count. So we'll do some examples. First one, sulfur has 16 electrons. We'll start the orbital diagram with 1s2, 2s2, 2p, 6, that takes us up to 10 electrons, 3s2, 3p4. And you look, all of those are paired all the way until the end. How many unpaired? How many singles? 2. 2 unpaired electrons. Let's do another one. Potassium has 19 electrons. Start the electron configuration the same way we did sulfur. 1s2, 2s2, 2p6. Now we're up to 10 electrons. We need 9 more. 3s2, 3p6, 4s1. So you look, all those are paired. 1 single electron, there's 1 unpaired electron. And what you can notice from these last 2 configurations that we've done is that if there are going to be unpaired electrons, they happen or they show up in the very last portion of your electron configuration or of your orbital diagram. So once you get a little bit more comfortable with this, you can do the electron configuration up until the last part, and then you only have to draw the picture for the last portion of your configuration. So let's do manganese, which has 25 electrons, and we would go 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d5. And if we are going to have unpaired electrons, they'll show up in this last portion of the electron configuration. So that's all I need to draw is the 3d5. Remember, a D has 5 houses or 5 circles, and you spread out the electrons as much as possible before you pair them up. So how many single electrons are here? 5. 5 unpaired electrons. Last piece of miscellaneous information. It is also sometimes helpful to be able to tell which atoms have been put into an excited state versus the ground state. Excited means that at least one or more of the electrons have been given energy and they have jumped to a higher energy level, and that's where they are. That's when they're in the excited state. So this happens when you put in things like heat, electricity. You saw this with the pickle last week. And we can actually tell which atoms have been excited just by looking at their electron configurations. And we can also use electron configurations to figure out what atoms or elements they are. So excited atoms are atoms that have electrons that have jumped to a higher energy level. And we'll do some examples. Again, you're looking for things in an electron configuration that almost appear to be out of order. It almost seems like there might be a mistake, but there's just an electron or maybe more than one electrons that have jumped to a higher energy level. So here's the first configuration, 1s2, 2s1, 2p1. If you know your order, you know that this electron right here should be down in the 2s, because normally we go 1s2, 2s2. So this atom is excited. This electron has jumped from the 2s up to the 2p. You figure out what atom this is by counting the electrons. 2 plus 1 is 3, plus 1 is 4. 4 electrons total. Look at your periodic table. That means this is beryllium. Let's do another one. 1s2, 2s2, 2p5, 3s1. If you know your order, you know that it normally goes 2p6 before you get to the 3s. So this electron right here has jumped from the 2p to the 3s. That means this atom is excited. Count the electrons to see what element it is. 2 plus 2 is 4, plus 5 is 9, plus 1 is 10. Check your periodic table. 10 electrons. This is neon. Another example. 1s2, 2s2, 2p3. Everything here is normal and in order, so this atom is not excited. This would be a ground state atom. Count the electrons to see what this is. 2 plus 2 is 4, plus 3 is 7. Check your periodic table. 7 electrons is nitrogen. And we've got one more to do. 1s2, 2s2, 2p6, 3s1, 4s2. This one has a couple of electrons that have jumped. Both of these electrons came from lower down. One of them came from the 3s, and then after 3s comes 3p. So 2 electrons have jumped here. This is an excited atom. Count the electrons to see what it is. 2 plus 2 is 4, plus 6 is 10, plus 1 is 11, plus 2 is 13. 13 total electrons is aluminum. And now you should be caught up. We've got a little bit of coloring notes we're going to do this coming week, and we'll see if we can put those online somehow, maybe. And then after that we'll be testing at the end of this week.